can see that as well. Okay, we are now recording, and the question was, where did I load test 3? And I couldn't remember if I had or not, but it's under Math 112. When you go to that, go down to weekly activities, click on that, go to week 13, click on that, and then under week 13 you'll see a test 3 tab. Click on that, and this is what you'll see. And there is the quiz there. Now I'm going to pull out of that unless someone else needs to see it a little bit longer. You'll see it going in backwards thing here. Here we are at test 3. When I click out of that, you see here's week 13, test 3. That's where you click there. And then I'm going to click out of that. And, ooh, that went too far, didn't it? Okay. I thought it was going to go back one more. Now, I'm going to show you one other place. I can't remember if I put it here or not. So let me try under messages. Let's see if I put it there. No, I forgot to put it there. Would you like to have it here? It's easy to put there. I'm going to click on the plus sign here, put all your names in, all course members, and we'll click on this, insert local file, and now I got to move your names out of the way again. Where do I move you? I think I'll move you to the bottom. Okay, let's try you down there for a moment. And we'll go to Math 112, Quiz 2, PowerPoint. Not PowerPoint, Word. Okay. And I'll put you in there too. Now I didn't put a piece of graph paper there. You can go back to either of the other two tests and get a piece, the graph paper there. Like here at the second test, you can go back and get the piece of graph paper there. The first test, so I think you can find graph paper if you need it, because I think you do need it. I just forgot to attach it here. Well, let's see, maybe I can easily. Let me attach that too. Let me see if it'll go back to that. Yeah, there's the graph paper. I don't think it's a very good copy of graph paper, but if you don't have any other, we'll put it there too. Okay, there's graph paper in there. So here's attached is a copy of the third test and a piece of graph paper. It's not very good graph paper, but there it is. So you have to scroll down a little bit here to see the test. There it is. There's the test. It says quiz 2, but it's test 3, and there's the graph paper. All right, so I'm going to send this to y'all now. So there it'll be under Blackboard messages, as well as under weekly activities, week 13, test 3. It'll be there too. So it's there in two places. So thanks for asking. I'm going to move y'all again back over here. Anyone else need to see anything in Blackboard while we're here? Okay, if not, D, I guess, I don't know when that was that a week ago or so? It looked like he couldn't get in, but I think you got here, didn't you? Okay, so anyway, I'm going to get out of Blackboard for now. And let's go back to class. Okay. Now it's going to take me just a minute to set up here. We're going to start with 2.4, and I think we're ready to go with that. So I'll go on and start sharing with that. And we might use the whiteboard, so I'll go on and set that up. means moving things out of the way. Okay, there's a whiteboard. All right, let's go back to 2.4. Okay, and we'll begin from current slide. Now, originally, when Shay asked her question, I was afraid I had forgotten to put, now let me just check again and make sure I've got everybody here. I've been occupied doing other things. We should have 14 students here, so let's see if I do. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. No, I'm missing somebody. Okay. Anaya, I think I forgot to put Anaya's name down. I saw her come in. What's that? Okay, I can't hear you. A little louder. Oh, were you talking to me or someone else? Was it Kanisha? Okay. All right. All right. I think I've got everybody marked present now. Okay. I'm trying to remember where I left off. Okay. When Shay asked her question, I was afraid I may have forgotten to load the test, and here's why. And I'll try not to take too much time with this, but I hope it'll help explain a few things that I didn't even understand before. And I'm going to give way too much background, but I'll give it anyway. Back in January of this year, right before classes started, I had a treatment for my leukemia, you know, the high white cell counts. It was a very, very effective treatment. Everything went really well. I was supposed to go back in March or sometime like that to have things checked, and they did, and my counts were way, way low. Not really super low, but they were low enough. But it did knock down some red counts and things like this, but it always does. Okay, so anyway, I was a little anemic and stuff, but I was able to function well. Okay, anyway. All right, well then we went back and June time frame, somewhere in there, and by this time COVID had gotten really scary. Okay, not as scary as it is now, but we didn't know that. We, at the time, it was really, people were really, really concerned, and my counts, my white cell counts had gone up to about 19,000. They should have been at max 11,000, but the doctor said, hey, it's not worth it. Stay home, because he knew it was going to knock other things out. And so yeah, we'll just live with this for another 3 months. Well, I went back in 3 more months. That would have put us in the September time frame, September, October, sometime like that. And that time the counts had shot up incredibly. 140,000 or something like that. They should have been 11,000 at the max. He said, you need a treatment. And at that high counts, he did a 2-day treatment. The first day was, is this somebody else coming in? I can't tell. Nope, I don't think so. Okay. So we did 10% treatment on the first day. That was a Thursday. If you remember, a couple weeks ago, or no, about 4 weeks ago, we missed a class because I had to go in for a treatment. And I could tell that day it was doing a number on the white cells. I could just feel it inside of me. I was hot. It was, I knew things were going on, and I figured they were good things. Well, I went back the next day for the 90% treatment, and I thought, wow, if that was the first day, 10%, what's today going to be like? Well, it was okay. It was not nearly as severe as the 10%. So I figured they had knocked out most of the cells with the 10%. And that's the last I saw of them. But right before the treatment, when my white counts were so high, I was, and he told me then I was very, very anemic. and I think I've told y'all that. And then when I took the treatment, got the treatment on that Thursday and Friday, I sensed that my red cells went even lower, so I was even more anemic. So I have been dragging for the last close to 4 weeks now. Okay, really dragging, and so I was supposed to have treatment tomorrow. So on Sunday evening, I sent a message saying, can I have my blood work done on Wednesday rather than waiting till I go to the lab on Friday to get the treatment? And they didn't answer Monday, and finally around 5:45 or something like that, they finally answered on Tuesday and said, yeah, we've cleared it, go on and get your lab work done. Because I knew I was feeling better than I did right after the treatment, but I was still feeling very weak, very exhausted, very anemic. I knew I was, okay? And so they approved me to do that. I went in on Wednesday morning to get the blood work done. And I think it was while I was driving home from the clinic, I must have gotten 3 messages from the nurse, because when I got home and checked it out, I saw that I had 3 missed calls. So, I didn't check immediately, but sometime later I did, and I picked it up to see what it was about, and the talked with another nurse. The one that had called me was busy doing something else, so she read me what the one had put on the portal, that I was extremely anemic. Okay, now this is 3 weeks after the treatment, and I was getting stronger every day. I don't know what I was right after the treatment. It must have been really bad, but extremely anemic, and I needed to come in and get typed and something else for a blood transfusion. So no treatment tomorrow, none. Okay, none whatsoever, because the Gazyva, the monoclonal antibody, had done such a good number on the white cell counts. They were way below what they should have been. The minimum level was 4,000. I was at 1.4 thousand, about a quarter of what they should have been. And it had knocked down my red cell counts. That's why I needed the transfusion. It had knocked down my platelets. That's why I needed the transfusion. And I'm also going to get a shot tomorrow for the neutrophils, which are the things that fight infections, because they're almost not, well, they're there, but not very many of them, not nearly what they're supposed to be. So the bottom line is, if I've been sounding like I'm tired and that kind of stuff, it's been true. I have been tired. I just didn't know how tired I was until I found this out. And number 2, tomorrow I'm supposed to have office hours between 8 in the morning and 12 at noon. I'm probably going to be at the clinic just about all those hours. I think my appointment is at 8, so I'll be there by 8. And then they say it takes 2 to 4 hours to do the transfusion. They've got all sorts of stuff to do ahead of time, and they do it slowly and all that kind of stuff. But they say I'm supposed to feel so much better. It's going to be incredible. I can't wait. So anyway, don't expect, what I'm going to be doing is carrying all my test stuff. I'll be grading papers while I'm in the clinic, but a lot of times I can't get a good signal, so I can't get the internet from the clinic. Or even if I can get it, sometimes I can't get to Blackboard or other things like this, because that's a, whatever they call it, open source or non-secure or whatever, and so sometimes I can't get into the systems. So I may be able to do some work while I'm there. I'm hoping to, but I may not be able to have any output into the system. So anyway, that's why things are as they have been and as they are, and hopefully I'll be getting better in the future. Okay, do y'all have any issues, concerns, problems that you want to bring up before we start class today? Yes, technically we've started class, but anything before I start on example 1? Okay, we're in chapter 2 polynomial and rational functions. We're in section 2.4, complex numbers, which was not in our course description. Okay, and since it wasn't in the course description, I'm sort of flying through this. The main reason I'm even covering it is you may need it in the future. Okay, you probably will even need it in some of the problems in this class, but I'm going to try not to test you on this. But if you do homework and stuff like this, you may bump into this. So we talked last time about how you add and subtract complex numbers. And basically my approach to this, and I've never really seen a book say this, and I don't know why they don't. It's just like adding binomials, because this is a binomial. You have a real term and an imaginary term, a real term and an imaginary term. So just treat it like a binomial. Add the reals, 4 plus 1, add the imaginaries, 7 minus 6. That would give you 5 plus I. That's it. Okay? The thing of removing parentheses and doing like grouping, they even call it this, grouping like terms. That's exactly what we're doing. Now this is a little bizarre here. This I should not be here. It should be 7 minus 6 with the I on the outside. Okay? So this is a little error. I don't think it's that way in your book. Yeah, they got it correctly in your book, but this I should not be there. Whoever did the graphics messed that up. That's 7 minus 6i. It's 7i minus 6i, and if you factor out the I, it's 7 minus 6 times I. I wouldn't have done that. I would have just said 7i minus 6i is I. Okay? And that gives you 5 plus I. There it is. Just that simple. Okay? Let's just do the second one because they started out for you. Here's the B one. 1 plus 2i. Now they put parentheses just to show you that's a complex number. Plus 3 minus 2i. Okay? Now, they write it without parentheses. I don't know why. I would just add like terms. Okay? 1 plus 3 is 4. 2i minus 2i is 0. There's your answer, 4. Done. Okay? Now, let's watch how they do it. I'm going to clear my scratch. Any questions on this so far? I know I'm going fast, and it's mostly because I'm not going to test you on this, but you might need to know how to do it in the future. Okay, sorry. Okay, so they wrote it without parentheses. I don't know why they put that in as a step. It's not necessary. Okay, I think I do know. Then they add like terms. Okay, 1 plus 3 is 4, and 2i minus 2i is 0. You see, that time they took out, they didn't write the extra I in there. So I'm going to come back up here. Yeah, there it is. And scratch this out again just so you'll know that I shouldn't be there. Okay, and that gives you 4 plus 0i, which is totally unnecessary to write 0i, so they just write it equal 4. Okay, now let's move on to the next one. Now, here they have a string of them. Now, this is the reason they removed parentheses before, to help you from making errors. Okay, this one doesn't have a real part. That's just a pure imaginary number, 3i. There is no number in front of it. And this time we're subtracting. Okay, the one we're subtracting is minus 2 plus 3i. That has both a real and imaginary component. Then we're subtracting from that yet again 2 plus 5i. Now, their deal of removing parentheses, when it's a plus sign in between, it's no big deal. When it's a minus sign, it's a bigger deal. So basically you just bring down the 3i, that's where that comes from. Minus times minus is plus 2. minus distributed over here to a plus becomes a minus 3i. This minus distributes in here to be a minus 2. This one distributes in here to be a minus 5i. Now we combine like terms. Okay, we have a 3i minus 3i, that adds to 0, leaving us a 5i. Well, let's hold on for that for a minute. Here we have a plus 2 and a minus 2, that adds to 0, so your answer is minus 5i. A pure imaginary number, no real part to it. Okay? Make sense? Let's see how they do it. They don't give the wording at the end. They combine the real parts, plus 2 minus 2, and they combine the imaginary parts, 3 minus 3 minus 5. Okay? And then this will be, if I were doing it, I wouldn't spend my time writing this over and over. That gives you 0. These two give you 0, and your answer is minus 5i. And they write the 0 first and then do minus 5i, which is simply negative 5i. Okay, there's the C part. Let's go on and do the D part. The D part here says 3 plus 2i plus 4 minus I minus 7 plus I. Okay? Now, again, you can remove parentheses if you want to. It's pretty simple. And if you're removing parentheses, why don't you go on and group like terms at the same time? 3 plus 4 minus 7. 3 plus 4 minus 7, which I think you can easily see that's going to turn out being a 0. Then let's group these. 2i minus I would be I plus I. That's going to be a 0. Now I'll write it the way they do. I don't particularly have a special reason for doing that. That would be a 2 minus 1. Whoa, I said it wrong. Yeah, no, minus I, minus 1. Because this is a minus sign there. Why that keeps showing up, I don't know. Okay, this is a minus I. So that's 2 minus 1 minus 1i. And guess what that adds to? Nothing. Okay, 0. 3 plus 4 is 7 minus 7 is 0. 2 minus 1 minus 1 is 2 minus 2 is 0i. So that gives you absolutely 0 as your answer. Okay, I'm on the wrong thing. Okay, should go over here, and I'll go and erase all this, and let's see how they did that one. 3 plus 2i plus 4 minus I minus 7 plus I. When we remove our parentheses, that's 3 plus 2i plus 4 minus I, but then this one, you distribute the minus sign inside, minus 7 minus I, then group your like terms, 3 plus 4 minus 7, that would give you 0. 2i minus I would be an I, minus another I is 0. That's all, folks, okay? They do a bit more work here, putting the 3 together, 3 plus 4 minus 7, and 2 minus 1 times I, factoring out the I, and they see this adds to 0, that adds to 0, 0 plus 0i, which is simply 0. Good deal. All right, any questions on how to add, subtract complex numbers? There is a checkpoint there. If you want to do the checkpoint, you certainly can. Just know you're probably not, I'm not going to test you on this stuff, but I'm not going to say you won't run into it somewhere in the future. So you decide whether you want to do that. All right, let's move on to the next slide. Many of the properties, this is on page 147 by the way, okay, if I haven't said that, chapter 2, polynomial and rational functions, 2.4 complex numbers, page 147, top of the page. Many of the properties of real numbers are valid for complex numbers as well. For instance, they don't give all of them, but they give a few of them. Addition, subtraction, and we haven't talked about multiplication yet or division, but of complex numbers, they're all what they call closed. That if you add two complex numbers together, you're going to get a complex number. Now remember, a real number is a complex number, okay? So everything that works for reals pretty much works for complex as well. So they didn't mention that one. The addition, subtraction, multiplication, and division will all be closed in the complex number system. If you add, subtract, multiply, or divide complex numbers, you will get complex numbers. Okay, understanding that real numbers are complex numbers. Another is the commutative property of addition and multiplication. Okay, if you change the order of which you're adding, doesn't matter. You're still going to get the same result. If you change the thing in multiplication, the order. Now we haven't talked about how to multiply yet, but it's still going to work. Okay, it's not going to matter. Now, just like in real numbers, if you change the order in subtraction, you got a different number. Okay, that is not, subtraction and division are not commutative. Neither are they associative. Only addition and multiplication. It doesn't matter which way you group things. If you're adding or multiplying three complex numbers together, then you're going to get, it doesn't matter which way you group them. They will all work out the same. Also, the distributive property of multiplication over addition. We've already been doing that, believe it or not. When we were distributing our signs across the parentheses, we were using the distributive property of multiplication over addition. So those are examples that still work. There are others. There's a zero product principle. There's a zero identity element. There's the additive inverse element. There's a multiplicative inverse element. Well, let's see. I don't want to go too far with that one. The multiplicative identity element. They're all there in general. I don't want to say all. There may be one or two that you don't do in complex numbers. I can't think for now if there is one, but most of the time they will work. Okay. So here is the next operation, multiplication. Notice below how these properties are used. Let's see. I think we skipped something there. Okay, let me go back. No, that's in the right place. Notice below how these properties are used when two complex numbers are multiplied. Now I don't think we hit this before, but let's hit it right now. Remember I said treat a complex number like a binomial. You're multiplying this binomial times that binomial. Well, what is our simple little way of doing that? Foiling it. First times first. Now, the only difference here is, well, they're distributing like that. But if you just use FOIL, that works. Okay, I'll show you that on this side. Because these are always binomials. A times C is AC. Okay, that's the first. Your outer is A plus DI. I mean A times DI. Okay, your inner is plus BCI. And your last is plus BDI squared. Now that I squared is the big difference here. Does anyone remember what I squared is? I squared is, it's going to take a while to get back there, but I want you to see it because you've seen it before. Oops, there it was right there. I squared, if I could get my pen to show. I squared is equal to negative 1. These two things you need to remember in imaginary complex numbers. I is the square root of negative 1. I squared is equal to negative 1. So you go back here to what we were doing with multiplying. Whoops, I went too far. And this becomes, this term right here becomes, because I squared is minus 1 minus BD. That's it. So what do we wind up with? You wind up with a AC minus BD, that's your real part, plus, and I'm going to put in parentheses, AD plus BC times your imaginary part. There's your real part, there's your imaginary part. Okay? And that's exactly what they get here. They do a lot more steps than we did, but AC minus BD is the real part, AD plus BC times I is the imaginary part. And you use those properties, associative, commutative, distributive, and the fact that I squared is equal to negative 1. Now, don't try to memorize that multiplication rule. That's waste of your memory, okay? Simply FOIL it, okay? It says, remember how you use the derivative property to multiply two complex numbers? Don't even mess with that. FOIL it, and it works out. Just remember I squared is minus 1, okay? So let's do this one. Okay, now this is sort of bizarre. This is a complex number, but it is a monomial, a real part only. So all you do here is distribute. Minus 8 plus 12i. Done. Okay, well that's what they've done here too. 4 times minus 2 plus 4 times 3i, and that is minus 8 plus 12i. Okay? I wouldn't have written an extra step there, but if that helps you see it, write it. Okay? Do whatever makes you see it best. Okay, here's another one. Now this one is, I think, much easier to do by FOIL. FOIL here. Now, I say FOIL, we're going to change the order a little bit. This is plus 8. Got it? Go straight to the last. Okay? Do the last part. We're not going to spell FOIL right anymore. This is minus I times 3i. That would be a minus 3 times I squared, but I squared is minus 1. Minus 3 times minus 1 is plus 3. There's your real part right there. I'll even put it in parentheses. Now do the inner and the outer. Okay, so let's do the outer first. That would be plus 6i, and the inner is minus 4i, and that would give you 11 plus 2i. Done. They go through and do this distributive, and look, if this makes more sense to you, doing it this way than foiling it, by all means do it. Do it the way, well, I'm on the wrong pad. Do it the way that makes more sense. If that makes more sense to you, do it that way. If foiling it, but misspelling foil, doing first and last first, then the outer and the inner second, and then combining like terms, if that helps you, do it that way. However you understand it most. So let's see what they get when they carry that through. They get 8 plus 6i minus 4i minus 3i squared. Okay, that's perfectly fine. It's correct. And then what do they do here? They substitute in the I squared of a minus 1, and that's all they did in that step. Then they grouped their real parts, 8 plus 3 together, and plus 6 minus 4i together, which we did right up here in 2 steps. They did it in 4 steps, and that gives them 11 plus 2i. Same answer we got. So do it however makes the most sense to you. So there's example 2B, here's C. All right, now this is a fun one. I suggest go on and do the foiling, but do it judiciously. 3 times 3 is 9. Then do the last, okay? And that's plus 2i times a minus 2i. That would be a minus 4 times I squared. Well, minus 4 times I squared is plus 4. Wait, yeah, because minus 4 is minus 4. I squared is minus 1, so that's going to be a plus 4. Now do your outer. Minus 3i, minus 6, I can't multiply, minus 6i, and look at that one, plus 6i. Look at that. This gives you 13 plus 0. Okay? Now, doing it their way, I guess this is distributing the 3i times this plus the 2i times that. That's what they're doing. And that gives them 9 minus 6i plus 6i minus 4i squared. I think that's how they're going to do it. And then they notice that the I squared is a negative 1. So that would be minus 4 times minus 1, which is plus 4. The real part's a 9 plus 4. Nope, they do it another step there, perfectly fine. And then these add to 0. Minus 6i plus 6i adds a 0. This gives you a plus 4, and you get 13, which is what we got way up here. Okay? So, any questions on that? Now, I want to point this out to you, what you've just done. You multiplied 3 plus 2i times 3 minus 2i. Now, I don't know if you remember giving this a name before, but if you don't remember that, let me tell you what to call this from now on. Now, I'm going to take you back memory lane here and do an A plus B times A minus B. We did this way back probably in developmental algebra, or possibly in Math 100, maybe in high school, somewhere like this. You knew the answer to this was A squared minus B squared. Anytime you multiply the sum times the difference of the same two entities, you're going to get the difference of their squares. Okay? Now that's what we used to call it. I'm going to give you the new name for it. You multiplied this number by its conjugate. They didn't call it that back then, but it is. The conjugate means keep the same first number the same, and the second number just change the sign. So A plus B is the conjugate of A minus B is the conjugate of A plus B. 3 plus 2i is the conjugate of the complex conjugate of 3 minus 2i, and 3 minus 2i is the complex conjugate of 3 plus 2i. Now, another context we did this if we did the square root of A plus the square root of B times the square root of A minus the square root of B. Okay, that is also multiplying a number, an entity by its conjugate. And what do you get? A times A, or square root of A times square root of A is A, and square root of B times the square root of B minus the square root of, that would give you minus B. Okay, same thing that we did here, we're doing here. Now that we used when we were rationalizing a denominator. You multiply by its conjugate. If one of the binomials was in a denominator and it had a radical in it, multiply by its conjugate. That's where we use the term, and that gave you a rational number. Okay, I was going to say integer, but it wouldn't be guaranteed to be an integer. It would be a rational number. These could be irrational numbers. If you put them under square roots, they're usually irrational numbers. Okay? So if you multiply by an irrational number by its conjugate, you get a rational number. Okay? If you multiply a complex number, where is it? Right there, by its conjugate, you get a real number. Okay? Hey, I'll take them. That's what we use conjugates for. Keep the first term the same, the opposite sign on the second term. That's the conjugate. Okay. Now here's another one. 3 plus 2i squared. Now you could take it this way and write them here. And if you did, I'd do the first. That would be a 9. And then I would do the last. That would be a plus 4i squared. Okay. Reason I did this is going to turn out being a real part. Then I do the outer part. That would be plus 6i. And then the inner part, another plus 6i. Okay. And what do you have? Oh, here comes Ladarius. He was here before, but he's come back. I guess he got booted out or he had to leave, but I already have him marked here. So we should still be at, where is it? 13 students. Let's see if we are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Uh-oh, we've actually lost somebody. We did have 14 students at one time. Okay. So what do we have here? 9. Okay. Because I squared is a minus 1, plus 4 times minus 1 would be a minus 4, and then you have plus 12i. So this would be 5 plus 12i. Now, there's nothing really magic here, but there's a simpler way to do it. Square the first term. This is what's true in all binomials when you square the first term is 9, plus twice the product of the 2. That would be 2 times 6i, which would be 12i. Then square the last term. Now squaring that makes it a minus 4, because that I squared is always a minus 1. Before, when we had just a regular binomial, the last term would always be positive. In complex numbers, that last term is going to be a negative real number. Combine these two together and you get 5 plus 12i. Now that to me is a little awkward. Do it however you want to, but you get the same answer. Let's see how they do it. That's probably, they find a more awkward way to do it, but let's see what they get. They first distribute, they say, and to me this is such a pain to do it this way, but it's fine. And then they distribute again. That would be a 9 plus 6i plus 6i plus 4i squared, which I'm sure is what they're going to get. And then they note that 4i squared is minus 4, so it's 9 minus 4. Well, there they did, the I squared is a minus 1, and that's what you get. They take a lot of steps to get there, but 9 plus 12i minus 4, and then 9 minus 4 is 5 plus 12i. So they took a lot more steps to get there, but they got the same answer. Okay? Always write it in standard form. Okay? Any questions on that? There's example 2. Okay? After every example, there is a checkpoint. I'll leave it up to you whether you want to do that or not. All right, now we're going to talk about our complex conjugates, which I already pointed out to you we did in the last set of exercises. Okay? Notice in example 2C that I pointed out to you, the product of two complex numbers can be a real number. Okay? That occurs with pairs of complex numbers of the form a plus bi and A minus BI. Those are called complex conjugates of each other. If you didn't have the I in there, you would call that conjugates of each other. If you had radicals in there, you'd call it conjugates of each other, but you use that to rationalize. You would take an irrational expression and make it into a rational expression. When you have just real numbers there, a plus b times a minus b, you just get the difference of two perfect squares. Okay? And when you have the complex conjugates, multiply those together, you're going to get a real number. Okay? And this is what happens. The a times a is a squared. bi times minus bi is minus b squared times I squared, which is a minus 1. Okay? And then the other two terms are your innards and your outards. The outer would be minus ABI, the inner would be plus ABI. They add to 0. Every time they add to 0, so you lose the imaginary parts, you're left with only two real numbers, and they are always both positive. A squared, of course, is positive, and where you had a minus bi squared look like it was going to be negative because I squared is a minus 1, it becomes positive 2. So there's your a squared plus b squared. Now, that leads to another issue here. Like I said before, when I started this thing, I said if you had a plus b times a minus b, that gave you a squared minus b squared. Every time, difference of two perfect squares. But remember then when we had difference of two perfect squares, we said you can always factor that to be a plus b times a minus b. But at the same time, we said if you have the sum of two perfect squares, you can never factor it. Never. That was in the real number system. In the complex number system, now we have a way to factor it. If you have the sum of two perfect squares, it will factor into two complex numbers, and they will always be complex conjugates of one another. Okay? So now, believe it or not, this little step exercise we did here also gives us a way to factor something we never were able to factor before, the sum of two perfect squares. Yeah, they factor to be the product of the conjugates of their square roots. Okay, the complex conjugates of their square roots. So, to write the quotient, now we're going into, let me make sure I'm not skipping steps here. I think they are. Let me see. This book is pretty bad about skipping steps. Okay, there was that. They're skipping example 3 and 4, I think. No, they're just skipping example 3. So let's us do example 3. On the whiteboard, which hopefully is still set up, ready for us to go. How are we doing on time? Okay, we got some time here. Okay, let's do example 3. Multiply each complex number by its complex conjugate. Okay, so here's 1 plus I. How would you multiply it? Number one, what is its complex conjugate? Anybody? If you're trying to answer, turn on your mic. If I put you all to sleep, I'll answer for you. That would be 1 minus I. Okay? So first you identify what the complex conjugate is. Same first number, opposite sign on the second number. And then how do you multiply those? You basically do half a FOIL. You could do a whole FOIL if you wanted to, but you're only going to use half of it. That would be a 1, and then this would be a plus 1. Because I squared is minus 1, Plus times minus is minus, so that would be minus of minus 1, which is plus 1. That's 2. Now, the reason we only did half of it, this one, the outer is going to be minus I, the inner is going to be plus I. That's always going to add to 0. Okay. The B part here says multiply each complex number by its complex conjugate. Here the complex number is 4 minus 3i. Get out of there. Minus 3i. First, what is the complex conjugate? Does someone want to chip in now? What's the complex conjugate of 4 plus 3i? Still silence. The sound of silence. Simon and Garfunkel. Many decades ago. 4 plus 3i. Okay. Then how do you multiply them? Multiply the reals. That gives you 16. Multiply the imaginaries and change sign, because I squared is minus 1. Minus 3 times plus 3 is minus 9. That would be 16 plus 9. You could think about doing the other two. That's a plus 12i minus 12i adds to 0. So this is 25. There's your answers. 2 for the first one, 25 for the second one. There's a checkpoint after that one as well. Okay, so now let's go back to the PowerPoints. Okay, 12-4. 2-4. Good buddy. Okay, and we'll go resume the slideshow. And we did this slide. Here comes the next slide. This is in between example 3 and example 4 on page 148. To write the quotient, now we've talked about adding, subtracting, and now multiplying complex numbers. How in the world do we divide complex numbers? To write the quotient of a plus bi and c plus di, now again, the one that's on top, the quotient, the one that's on, when you're doing your division, the one that's mentioned first is on top, the one that's mentioned second is on bottom. Or if you're doing by your old division sign, this goes outside the house, that goes inside the house. But here, far better to put them over each other. This one over that one. In standard form, where C and D are not both 0, because guess what? Even in the complex number system, you cannot divide by 0. So C could be 0 and D not, or D could be 0 and C not, but they can't both not be 0. They got to both not be 0 at the same time. Now, how do you do that? Now, if you remember, back when we dealt with irrational numbers, like the square root of A plus the square root of B, I don't know why I put a parenthesis there, over the square root of C plus the square root of D. Okay, that was almost an impossible thing to do. How do you divide by something like this? Well, what did we do? We multiplied by the conjugate, the square root of C minus the square root of D. But if you multiply the denominator by that, you also have to multiply the numerator by that. And that's probably why I put my parentheses there, because then you do the square root of C minus the square root of D. Now, sure, that makes the numerator a little more complicated, but not badly. But this thing, this over itself is 1, so you haven't changed the value any, but this always produces C minus D, which is a real number. And whatever that real number is, we can divide by it. Okay? So that was our technique there. That's the technique here too. Multiply the denominator by its complex conjugate, but when you do that, you have to also multiply the numerator by the complex conjugate. Sure enough, that makes the numerator a little more complicated. A times C, and remember, because here this would be B times D, or minus D, which is minus BD times a minus I squared, which is minus 1. So that would be AD plus BD, AC plus BD. That's the real part, and the complex part would be in the outer and the inner, minus AD plus BC times the I. Don't memorize this formula, just get what you're doing here, but this one always gives you C squared plus D squared every time. So what have we got here? We have a real part over a real part. That's going to be a real part. And what do we have over here? A imaginary part, which has a real component times I over a real component. That's your imaginary part. Okay? This is your, so to speak, let's see, what would we call it? M plus Ni. Okay? This part here is a real number. That would be your N times I. This is a real number. That would be your M. So now you have it in standard form. Okay? And they like for you to get it back to standard form. Okay? That leads to example 4. 2 plus 3i divided by 4 minus 2i. Well, we can't divide by an imaginary number. You just can't do it. Okay? So make that denominator real by multiplying by its conjugate, complex conjugate. But if you multiply the denominator by that, you got to multiply the numerator by that. So this would give you 8 when you do the first part. Do your last part, and that gives you a minus 6. There's your real part of the numerator. Now do your outer, which is a plus 4i. The inner is a plus 12i. That would be plus 16i. Now do your denominator. And that's always easy. 16 plus 4. Multiply these two together, you get 16. Multiply these two together, you get a minus 4i squared, which is a plus 4. Okay, so what do you get here? That would be 2 over 20. That's your real part, plus 16 over 20 I. There's your imaginary part. This would be 1/10 plus, what is that? 8/10, which would be 4/5 I. There it is in standard form, in reduced form too. Okay, now I did that quickly. I hope I didn't make a stupid mistake. Let's see if I did. I'm going to erase this part first so you could read what they do. And they pretty much did what I did. They FOILed the top part, 8 plus 4i minus 12i plus 6i squared over 16 minus 4i squared. Why they took the time to write all that, I don't know, but you could. That would be 8 minus 6 plus 16i over 16 plus 4, which is indeed what we got. And that would be 2 plus 16i over 20. Now, I like that form really well. It's just simple. It's there. I would divide out the 2's, but the book always likes you to take it to standard form, which would be 1/10 plus 4/5 I. This over this is 1/10. This over that is 4/5 times I. They always love you to take it to standard form. To me, just factoring out the 2 everywhere here and make that 1, an 8, and a 10, that would have been okay too. 1 plus 8i over 10. Sure, this would simplify a little bit further, but I don't have any problem with that. The book always wants you to take it to standard form, and that's probably a good practice. I'm just sort of lazy. All right. Now we go to complex solutions of quadratic equations. This is the whole reason we brought up complex numbers, because what we've been doing is solving equations, coming up with solutions. What we're finding out, sometimes those solutions are complex. Okay? So you can write a number such as the square root of -3 in standard form by factoring out the square root of -1. Remember, that's the one I said always remember, I is equal to the square root of -1. So this would be, I do it the other way, but they do it this way. Where is my pen? Do you see it? There it is, I think, right there. Okay. What I would do was make this the square root of -1 times the square root of 3. They did it sort of backwards. And this would be I times root 3. Just do it like that. They always like you to put the root 3 in front. Okay? Now, here's why I don't like to do that. Because if you had written this, now when they type it, it's sort of clear, if I could find it, yeah, that square root sign ends right there. But if I did this, the square root of 3i, is that I inside or outside the square root? It's hard to see. That's why I like to write the I in front, square root afterwards. Then you know the I is outside the square root. Okay? Now that's maybe because I'm a sloppy writer. Okay? But I am a sloppy writer, so that's why I like to put it there. Now, another thing you can do is bring down a little vertical line here to indicate that I is outside the square root sign. That's a little awkward too, but it can be done. Now, we call that number the square root of 3i, or I root 3, okay, whichever you want to call it, is the principal square root of -3, okay? Just like the square root of 4. Wow, someone's doing some work in our alley back there, which is fine with me. I just saw some bamboo just being taken down, which I had planned to do after I retire, but I'm glad they're taking it down now. Never mind, I shouldn't have gotten distracted. Okay, so the disadvantage of facing the outside window here. I see when the trash truck comes by, when the recycle truck comes by, when the neighbor is cleaning up in the alley, whatever. Okay, so this is what we mean by the principal square root of a negative number. If a is a positive number, the principal square root of -a, that's obviously going to be a negative number then, would be the square root of a times I. Now what I was going to say, it's just like if you did the square root of 4. You say it's 2. Okay? That's the principal square root of 4. In reality, you know there's another square root of 4, and that's -2. But principal means positive, so the p's mean the same thing. So this is going to be your a, square root of a times root I. I'm sorry, square root of a times I. Okay, so I don't know that there's a real, yeah, let's go on and do it. It says solve that equation. You could try to factor that till the cows come home, and you're not going to be able to factor it. So what you'd have to do is use the quadratic formula. Now, if you haven't used this lately, let me give it to you. For your standard quadratic equation, ax, this is such an aggravating thing, ax squared plus bx plus c is equal to 0. That's what we call a quadratic equation in standard form. They love standard forms, don't they? Here's the solution. You can just write it down. X is equal to minus b plus or minus the square root of b squared minus 4ac, all divided by 2a. That's the quadratic formula. Okay? Now, of course, a is your quadratic coefficient, b is your linear coefficient, c is the constant coefficient. So, how would we do that here? X is equal to, here's your a is 3. If it helps you to write it down, write it down. B is minus 2, and C is 5. Okay? So let's write down what we've got. X is equal to minus B, so that would be a 2, because this B is minus 2, plus or minus the square root of b squared, which is 4, minus 4, that's always a minus 4 there, times a, which was 3, times c, which is 5, and you divide that by 2 times a, which is 3. Okay? Now, when you go to do this, this is 2 plus or minus the square root of 4. Now, what I do next is count the number of minus signs. You know you always have 1 because that's there. Now, if either one of these two had been a minus, then you'd have maybe 2. If both of them had been a minus, you'd have had 3. Well, why do I count the minus signs? If the number of minus signs is odd, like it is here, 1, that means this is going to be a minus. If that was even, like one of the others was a minus, but only one was, then you'd have had 2 minus signs, that would have been a plus there. As soon as you get a plus there, you know you're not going to have an imaginary complex number. You may have an irrational number, but it won't be complex. When you have a minus sign there, it depends on the size of this, and that's a big number. That's 20 times 3 is 60. Okay? That's going to be complex. I can tell you now that's divided by 6. Okay? So what is this? Now you can split this out now, or you can wait a little later. It doesn't matter when. That's going to be 2 plus or minus the square root of 4 minus 60 would be a negative 56. All divided by 6. Well, let's break that down a little bit more. 2 plus or minus. Now, what I like to do here, I know I've got a minus 1 there. So let's factor that out. Are there any perfect squares in 56? What you can do is do your prime factorization. 56 is 2 times 28, right? 28 is 2 times 14. 14 is 2 times 7. Is it time? Oh my goodness, how sad, how sad, how sad. Okay, so we will finish this problem next time. Thanks for telling me. I didn't know we had gone. I did run my mouth that long. We are on example 6. I think I just skipped example 5, didn't I? I'm sorry about that. We're going to start next time with example 5, not example 6. Let me erase what it got here. And you know, of course, next time, the bad news, folks, you know this, don't you? There are no classes next week. Get over it, okay? Next week is Thanksgiving week. The college will be open Monday, Tuesday, and Wednesday. I'll say that with a grain of salt here. I'll tell you why. We will be in professional meetings most of those 3 days, okay? So that means it may be sort of tough to get in touch with us, but you can get any business done you need at the college in those 3 days, with this exception, okay? Wednesday of next week, I would not plan on getting anything done at the college afternoon. There will be people there. The college will be open, but a lot of people will be taking off afternoon. Okay, it may be they'll give them the time off. It may be they'll be taking vacation time off. Whatever, You will not find everybody there sometime afternoon. They may be there till 1 or 2 o'clock, but at 4 or 5 o'clock, I bet you're not going to find very many people there at all. So if you have any business at the college, take care of it Monday, Tuesday, all day long. There'll be someone in every office all day long, Monday and Tuesday, or Wednesday morning. I guarantee you there'll be someone in every office Wednesday morning, but I will not guarantee there'll be anyone in the office or very many people in the office Wednesday afternoon. Okay? There will be some, I bet, but I can't tell you which office and how many people, and so don't bank on it. Get your business taken care of by Wednesday morning. Okay? Have a good Thanksgiving. Be safe this Thanksgiving. I know it's real tempting to get with friends, to get with family, and maybe it's a tradition, but look, folks, this virus is going out of control right now. It's far better to be healthy and be able to spend next Thanksgiving with your family members than to be risky this Thanksgiving and have a chance that somebody in your family may not be here next time. So please, folks, be careful. Be very careful. Okay? I want to see you all next week, okay? I mean the week after next. And the week after next is the last week of class, so we'll wrap up Chapter 2 next week, the week after Thanksgiving, and then I'll give you your final exam that Thursday morning or Thursday after class, and then we'll have any time that next week to turn it in. Okay? Any questions? Okay, any questions on the problem we were working on that we didn't quite finish? Going to stop sharing there, and I'm going to end the meeting for everybody, but again, I'm going to say I want to see you all back healthy on the week after Thanksgiving. So please be careful. Please be careful, okay? Take care. See you a week from Tuesday. Don't eat too much turkey, okay? Bye-bye.